Number one asks us to determine how many moles of hydrogen are needed to react completely with 2 moles of nitrogen. So just making some labels here, we have 2 mole of nitrogen, and we're asked to find how many mole of hydrogen is that going to need to react. So begin with our 2 mole of nitrogen. We're already at mole, we're just trying to go to mole of the other substance. Sorry, I wrote a gram there, let's correct that to mole. We have mole of nitrogen down the bottom. We're working our way to mole of hydrogen on the top. The coefficients are 3 to 1, so this is a 3 to 1 ratio. So doing the dimensional analysis here, this simply comes out to 6.00 mole of H2. We have 3 sig figs here to match the 3 sig figs from the problem, the information from the problem that was provided. Number 2 is similar. How many moles of oxygen, question mark, moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate? Well, this guy right here is potassium chlorate. We have 6.00 moles of it. So again, this is another mole to mole conversion, one step. 6.00 mole KClO3. We'll put the mole of KClO3 in the bottom to cancel out. And we're going to moles of O2. We have a mole on top of a mole, so we're looking at the coefficients. 3 O2s for every 2 KClO3s. Multiply across the top and divide by the bottom. So this comes out to be 9.00 mole of oxygen. Again, 3 sig figs in the answer because it's the 3 sig figs from the problem. Number 3, how many moles of hydrogen, so question mark, moles of hydrogen, are produced from the reaction of 3 moles of zinc? Be careful not to select this. We're looking at just zinc. So that's 3.00 mole of zinc. One more conversion, straight mole to mole, one step. 3.00 mole of zinc. We'll put mole of zinc on the bottom to cancel, working our way to moles of H2, and it is a 1 to 1 ratio. So this is a pretty straightforward one. It comes out to 3.00 mole of hydrogen. Number 4, this one is not balanced. Let's go ahead and just balance it out first. I see 3 carbons here, only 1 here. I'm going to write this a little bit bigger, actually. C3H8 plus O2 makes CO2 plus water. So I know I'll need 3 here on my carbon. I see that I've got 8 hydrogens coming in sets of 2. That means I need 4 sets of those 2. And now balance the oxygens. 3 times 2 is 6, and 4 times 1 is 4 for a total of 10. So I need 5 sets of 2 in order for this to balance out. Now I can begin the actual problem. How many moles of oxygen gas, so question mark moles of O2, are needed to react with 4 moles of propane, which is the C3H8? 4.00 mole. One more straight mole to mole conversion. 4.00 mole of C3H8. Putting mole of C3H8 in the bottom to cancel. Mole of O2 on top. And I see it's a 5 to 1 ratio. So this will just come out to be 20.0 mole of O2. Again, 3 sig figs in the answer because of the 3 sig figs provided from the prompt. Number 5 is shifting gears a little bit. What volume of hydrogen? So we're looking for the liters of hydrogen are necessary to react with 5 liters of nitrogen. So we have 5.0 liters of nitrogen, and we're converting to liters of hydrogen. Well, just remember, at STP, 1 mole of any gas is equal to 22.4 liters. So that's going to be the conversion that we're going to use here. So we'll start with the one we know, which is 5.0 liters of N2. Putting liters of N2 in the bottom to cancel, going to moles of N2 on top. And as we said right here, 1 mole of any gas is 22.4 liters. Now, I'll put moles on bottom to cancel out, moles of nitrogen, that is. I'll put moles of hydrogen on top. And we're going from moles to moles, so we look at the coefficients. 3 moles of H2 for every 1 mole of nitrogen. And now we'll get rid of moles of hydrogen. We're going back to liters, this time liters of hydrogen. Again, 1 mole of any gas is 22.4 liters. So this is going to come out to be just 15 liters of H2. Now you might notice if you're paying extra close attention, you have a 22.4 on the bottom and a 22.4 on the top. So truthfully, that step's actually unnecessary because they just cancel each other out, which is why this ended up being just 5 times 3. But if you need to show this work to rationalize your way through it, that's okay. Number 6, what volume of ammonia is produced in the problem from, or in the reaction from problem 5? Well, that reaction, just to copy it over, was, let's look back at it. Okay. N2 plus 3H2, that's a 2, made 2NH3. And now we're looking for the volume of ammonia made here. So that's liters of ammonia produced from problem 5. That means we need to pull the information from problem 5. And you have two options. You can either just use the 5.0 liters of nitrogen that you started with, or you can use the 15 liters of hydrogen you ended with. Either way, it doesn't matter. You'll get the same answer. So I'm just going to go with the 5.0 liters of nitrogen again. This one's going to be similar. We're at liters, so we'll go to moles, then go to moles of the other substance and take that to liters. So 5.0 liters of N2, 22.4 liters of N2 is 1 mole of N2. Mole of N2 on the bottom, mole of NH3 this time on top, and it's a 2 to 1 ratio, 2 to 1. And now mole NH3 on the bottom, liters of NH3 on the top, 22.4 liters is 1 mole. Again, the 22.4 could technically cancel out, but don't worry too much about that. This comes out to be 10.0. Actually, there's only 2 sig figs there, so there wouldn't be a 0. This would just be 10 decimal point to make that 0 significant. 10 decimal point liters of NH3. Number 7, if 20 liters of oxygen, 20.0 liters of oxygen are consumed, how many liters of carbon dioxide are produced? So question mark liters of CO2, 20.0 liters of O2, liters of O2 on bottom, mole of O2 on top. 1 mole is 22.4 liters. Mole O2, mole CO2, 3 moles for every 5 moles of O2. So 3 for the CO2, 5 for the O2, and 1 mole of CO2 has a volume of 22.4 liters. So this is going to end up being to 3 sig figs 12.0 liters of CO2. Number 8, this one's not balanced. Let's go ahead and balance it first. I see that there's 1 carbon, but there's 3 oxygens and 2 oxygens. So we need to get rid of that odd number of oxygens on the left. The easiest way to do that is probably to throw a 2 right there. That'll give me 2 carbons, so I'll have to put a 2 here as well. And that actually will give me 4 oxygens on both sides, so the whole thing is balanced. So let's try the question now. How many liters of carbon dioxide, that's this one right here, so question mark liters, are produced if 75 liters of carbon monoxide are burned? Then it also asks how many liters of oxygen would be necessary to do so. So really, we're solving for both of these. We'll have to do 2 problems here, but I bet we can find a shortcut. Let's go ahead and do our 75 liters. And let's convert that to the CO2 first. So 75 liters of CO, 22.4 liters of CO for every 1 mole of CO. I don't want mole of CO, I want mole of CO2. And I see that it's a 2 to 2 ratio, which is the same as a 1 to 1 ratio. And then lastly, mole of CO2 on bottom, liters of CO2 up top. 1 mole is 22.4 liters. And this one's really particularly goofy. You just have a bunch of ones, and then you have your 22.4 on top and 22.4 on bottom. They're going to cancel out. So this is just going to wind up being 75 liters, 75.0 liters of CO2. Now you'll notice, since the 22.4 and the 22.4 are going to cancel, they're going to cancel whenever I go from CO to the O2 just as well. The only thing that will be different is this mole ratio right here won't be 1 to 1. Instead, this top number is still going to stay 1 because of the O2, but the 1 that we had here is a 2 because this ratio of these two is a 2 to 1. So what's going to end up happening is you'll find that you'll need half as many liters of O2 as you do CO. So really, this is just 75 divided by 2, and it comes out to be 37.5 liters of O2 that are needed for this reaction. Number 9 is our first one that's not involving liters or just moles. How many grams of potassium chloride? Well, this guy right here is potassium chloride. Make sure you don't accidentally select that one. So we're looking for grams of potassium chloride are produced if 25.0 grams of potassium chlorate, which is this guy right here, decompose. So this is a grams to moles to gram problem. So we'll start with our 25.0 grams of KClO3. Here we'll need the molar mass of this guy, so 39.10 for the potassium, 35.45 for the chlorine, plus 16 times 3 for the oxygens, is 122.55 grams of KClO3 is equivalent to 1 mole of KClO3. On to the mole ratios. I want the mole of KClO3 to cancel. Sorry for the handwriting. I'm going to moles of KCl, and I see it's a 2 to 2 ratio, so that's just a 1 to 1 ratio. We'll leave that just like that. And then 1 mole of KCl is, again, we'll need their molar masses. It's 39.1 plus 35.45 for a total of 74.55 grams. Plugging this into the calculator, multiply across the top, divide across the bottom, you get 15.2 grams of KCl. Number 10 is similar. How many grams of hydrogen? So I'm looking for grams of hydrogen are needed to react with 50 grams of nitrogen, 50.0 grams of nitrogen. Another gram to mole to gram problem, 50.0 grams of nitrogen. Don't want grams of nitrogen, taking that to moles of nitrogen. I need the molar mass here, 1 mole. Be careful, it's diatomic, so it's actually 2 nitrogens, 28.02. Canceling out mole of nitrogen to the bottom, going to moles of hydrogen up top. It's a 3 to 1 ratio. And then canceling out the moles of H2. I'm going to go to grams of H2. Again, I need the molar mass, but this guy's diatomic, so it's really 2 hydrogens for a total of 2.016 grams of hydrogen. Multiply across the top, divide across the bottom, you get an answer of 10.8 grams of hydrogen. You would need 10.8 grams of hydrogen to react with 50 grams of nitrogen. Number 11, how many grams of ammonia are produced in problem 10? Again, that reaction was N2 plus 3H2, make 2NH3, and I'm looking for grams of ammonia. This is similar to the previous a few problems ago. You can either use the 50 grams of nitrogen and get an answer, or you can use your 10.8 grams of hydrogen and get an answer. I'd go with the answer that you didn't calculate, just in case you messed this one up in the previous problem, you know you're safe. So this would be 50.0 grams of nitrogen that we're going to take to grams of NH3. 50.0 grams of nitrogen. Grams of nitrogen to moles of nitrogen. 1 mole of nitrogen is 28.02 grams, just like it was in the last problem. Canceling out mole of nitrogen, this time going to mole of NH3. and it's a 2-to-1 ratio. And now 1 mole of NH3, we'll take that to grams of NH3. So that's nitrogen at 14.01 plus the hydrogen's 1.008, but there's 3 of them for a total of 17.034. Plug in this one in, multiply across the top, divide across the bottom, 3 sig figs, 60.8 grams of NH3. Which actually, had we been paying attention, we could have known because the previous question right here asked us to solve for hydrogen and it was 10.8 grams of hydrogen. So it makes sense that if 50 grams of nitrogen went in and 10.8 grams of hydrogen went in, mass has to be conserved. So that 50 plus that 10.8 has to give us an answer of 60.8. Number 12, how many grams of silver chlorides, question mark grams, are produced from 5 grams of silver nitrate reacting 5 grams, and it says this one's not balanced. So let's go ahead and balance it. I see 2 NO3s over here, but only 1 on the left, so I'll put a 2 here. That gives me 2 silvers, so I'll put a 2 here, which gives me 2 chlorines, which balances. So 5 grams of AgNO3. Since I don't want grams of AgNO3, that'll go to the bottom. I'm going to take that to moles of AgNO3. 1 mole, we need the molar mass. Silver's 107.87 plus nitrogen at 14.01 plus 16 oxygens times 3 is 169.88 grams. Putting moles of AgNO3 in the bottom to cancel. Putting moles of what I'm going for, which is AgCl on top. And I see it's a 2-to-2 ratio or a 1-to-1 ratio. And now 1 mole of AgCl. I need grams of AgCl. So we'll add the molar mass again. Silver's 107.87 plus that chlorine at 35.45 is 143.32 grams. Plugging this one in, top times top, bottom times bottom. You only have 2 sig figs this time though, so it's 4.2 grams of AgCl. Number 13 has some mixed problems here. What volume of ammonia, so we're looking for ammonia and volume is measured in liters, is produced if 25 grams of nitrogen reacts. So we're going to have to take this gram of nitrogen to moles of nitrogen. Then from there, take that moles of nitrogen to moles of NH3, and then take that to that mole of NH3 to liters. 25.0 gram of nitrogen. Grams of nitrogen to the bottom. Moles of nitrogen up top. 1 mole is 28.02 grams of nitrogen. Mole of nitrogen to mole of the target, which is NH3. It's a 2-to-1 ratio. Now be careful here. I'm trying to get rid of moles of NH3, but I'm going to liters. So I need liters of NH3 up top. And the ratio here is 1 mole for every 22.4 liters. Plugging it in and to 3 sig figs, you get 40.0 liters of NH3. Number 14, similar, very similar. 5 grams of potassium chlorate, which is this guy, 5.0 grams. What volume of oxygen is produced? So I'm looking for the volume, again, liters of oxygen. 5.0 grams, KClO3. I don't want grams of KClO3. I want moles of KClO3. Even though I just looked up this guy's molar mass, or we just calculated it, I can't remember it. So potassium's 39.01, no, 39.10, sorry, plus chlorine, 35.45, plus 16 times 3 for the oxygen, 122.55. I don't want mole of KClO3. I want mole of O2, and I see that's a 3 to 2 ratio, 3 to 2. And I don't want mole of O2 now. I need to take that to liters of O2. And there's 22.4 liters in 1 mole. Plugging this guy into 3 sig figs. Actually, we have 2 sig figs, sorry. 1.4 liters of O2. Number 15, how many grams of potassium chloride I produced in that previous problem? Well, that formula, their equation rather, was 2 KClO3 makes 2 KCl plus 3 O2. And we can use either one. We could use this 1.4. I don't love using that because we rounded it. I would go back and use the previous problem's 5.0 grams of KClO3 to answer the question, how many grams of potassium chloride are produced? So we're just looking for grams of this guy. This is a typical grams to mole to gram problem. 5 grams of KClO3. Don't want grams of KClO3. I need moles of it. 1 mole, we just looked it up, was 122.55 grams. Don't want mole of KClO3. I want mole of KCl. And it's a 1-to-1 ratio because of the 2 to the 2. You could put the 2 to the 2, but you don't have to. And 1 mole of KCl is, we just had this guy's molar mass as well, 74.55. 74.55 grams. Plugging this one into 2 sig figs, you get 3.0 grams of KCl. And number 16, the last question, I see it's not balanced. Let's go ahead and balance it. Let me write it a little bigger. LCl3, goodness, plus Al plus Cl2. I see a 3 here and a 2 here. We need to get that to the least common multiple of 6. So I'll need a 2 out front and a 3 out front here, which means I need a 2 here to balance that. If 10 grams of aluminum chloride are decomposed, 10.0 grams of this guy, how many molecules of chlorine gas is produced? So I'm going to have to use Avogadro's number here at the end because I'm trying to go to particles. So 10.0 grams AlCl3, grams of AlCl3 in the bottom, moles of AlCl3 on top. 1 mole, we'll add this together, 26.98 plus 35.45 times 3 is 133.33 grams. Mole of AlCl3. I'm going to moles of Cl2. It's a 3 to 2 ratio. And then last, I'm going to really run out of room here, but we'll do our best. 1 mole of Cl2 is equivalent to 6.022 times 10 to the 23rd molecules of Cl2. Since we're going to particles, we use Avogadro's number. To 3 sig figs, when you plug this in, you should get 6.77 times 10 to the 22nd molecules of Cl2.